Hello, it's time to get started on Module 6, where we will be talking a little bit about continuous random variables and how they're different from discrete variables. And we'll also, in this first part, look at a continuous random variable, namely the uniform distribution. Recall from an earlier module that a continuous random variable can assume any value in an interval on the real number line over some range. That means that the number of outcomes possible for a continuous random variable is infinite. Well, since the number of outcomes is infinite, it effectively means that the probability of any one particular outcome is zero. So we're not going to really be able to talk about the probability of a specific outcome the way we could with a discrete variable. With a discrete variable like the binomial, for example, flipping a coin, we had probabilities to individual outcomes, such as what's the probability of flipping 3 heads in 5 flips. But for a continuous variable, this will not be possible. If you don't see why, let me give it an example, sort of my standard classroom example. I often point at a light bulb and I say, what's the probability that this light bulb burns out in exactly 23 days, 14 hours, 16 minutes, 23.87 seconds from now? And most people will shake their heads and say, well, that's basically zero. And they're right. The probability of it burning out in exactly that amount of time is basically zero. But that's just one point out of an infinite number of points, is why it's zero. So we really can't talk about the probability of any one point out of this infinite number. We will be able to talk about the probability of an interval, as we'll see. Now, a continuous random variable is going to be depicted by something called its density function. We can depict density functions either graphically or by equations. For the most part, we will use graphs. The total area under the density function is going to be 1 unit, analogous to the idea that the sum of the probabilities equals 1. Get used to the idea with a continuous variable that probability equals area under the curve. Now, some of you might have had calculus in your life, and you might remember back to calculus that finding areas under the curve involves integration. Well, we don't want to be messing with integration in this course because most of you haven't had calculus. Fortunately, we won't have to. For the continuous variables that we'll look at, we will find other ways of getting the probabilities rather than using calculus. As I said a minute ago, the probability of a random variable being in some interval, say from x1 to x2, is now going to be the area under the graph of the density function between those 2 points. Let's take a look at a graph of a continuous random variable. Here we have a normal shaped distribution, which we will be getting to later in this module. Supposing I'm interested in the probability that the variable x falls between x1 and x2. We're going to define that actually as the area under the density function between those points. The complete density function will have a total area of 1 unit, and the part that we want here between x1 and x2 would be this shaded area. Get used to equations written in the following way. If I want the probability that the random variable x is between x1 and x2, I will normally write an equation in this way. One last little point that I like to make about the difference between a discrete variable and a continuous variable. For a continuous variable, it wouldn't make any difference whether I write the probability that x is bigger than or equal to a, or the probability that x is bigger than a, because the one point at a itself has no area and therefore no probability, as we saw a minute ago. That wasn't true for a discrete variable. For a discrete variable, take the binomial, the probability, for example, of 3 or more heads in 5 flips of a coin, which would mean 3 or 4 or 5, is different than saying more than 3 heads, which would just be 4 or 5. the equal part had some probability there. But here with continuous variables, it doesn't matter. Okay, now let's go on to a specific continuous distribution. Let's look at what we'll call the uniform probability distribution. Sometimes called a rectangular distribution because the graph of its density function is going to look like a rectangle. It gets the name uniform because over some range, let's say from point A to point B, the distribution is uniformly high. Here's what a uniform distribution looks like. We're going to measure f of x, the density function, on the vertical axis, and the variable x here on the horizontal axis. With a uniform distribution, the variable only exists from point A to point B. No values below point A are possible, no values above point B are possible. Now in this case, we can use our knowledge back from algebra and geometry to figure out some probabilities here. Remember, of course, the area of a rectangle is just height times base. So to make this a legitimate density function that has a total area of 1 unit under it, we would need this base, b minus a, times this height, which will be f of x. That has to equal 1. So I have that up here in this equation. B minus a times f of x must equal 1. This distance times this distance has to give us 1 unit. Solve that for f of x, and you get f of x has to be 1 divided by b minus a. So I've placed that right over here. The height of this function has to equal 1 over b minus a. So here's how we technically write an equation for this density function. F of x equals 1 over b minus a for any value of x in the range from a to b. And it's equal to 0 otherwise. Again, what that second part simply means is that the function only exists on the points from a to b. Let's go back to our graph. No values of x above b are possible, no values below a. So f of x is just 0 above b or below a. It might be kind of obvious what the expected value of a uniform distribution is. Let's go back to our graph. Remember, the expected value is the mean, and as you've learned in earlier modules, the mean is the balancing point of a distribution. Where would I have to put my finger to balance this kind of a distribution? Well, if you said right in the middle, you're correct. Since this is perfectly symmetric, the balancing point would be right in the middle. Right in the middle, though, is going to be a plus b divided by 2. So that gives us a formula for the expected value, a plus b over 2. There's also a formula for the variance, however, that involves calculus, and so I don't generally use it, and we really don't need it here at all. Let's do an example. Let's do a problem. Suppose a particular operation on an assembly line takes between 5 and 10 minutes to complete. Assume the time this operation takes is uniformly distributed over that range. Again, as soon as they tell you that it's a uniform distribution, you know that its density function looks like one of these rectangular boxes that we just looked at. And I ask you some questions here. What's the mean time this operation takes? What's the probability the operation takes 8 minutes or longer? What's the probability that the operation takes between 8 and 11 minutes? And I warn you to be a little careful on that last part, and you'll see why in a minute. Well, once again, let's draw ourselves a picture and see what this looks like. We're told that this operation takes between 5 minutes and 10 minutes. So that's our points A and B from earlier. Those are the endpoints of this distribution. Nothing below 5 is possible. Nothing above 10 is possible. We can figure out what f of x has to equal by the equation we had before. F of x has to be 1 over b minus a, where b is 10, a is 5. 1 divided by 10 minus 5 is 1 over 5, or 0.2. So the height of this function has to equal 0.2. The first part of the problem asked you for the mean. Remember, the mean is pretty easy. It's right in the middle. Right in the middle of 5 and 10 would be 7.5. And again, you could get that by just taking 5 plus 10 divided by 2. So the mean time that this assembly line operation takes is 7.5 minutes. Let's go to part B of the problem. Part B asks you what's the probability that it takes 8 minutes or longer. Well, remember, 8 minutes or longer will be equivalent to 8 to 10, because nothing is allowed above the point of 10 here in this example. The distribution ends at 10. So we want the probability between 8 and 10. Now again, if you remember, just probability is area under the curve, and the area of a rectangle is height times base. This base is 2 units wide. The height here is 0.2 in height. F of x is 0.2. You simply take 0.2 times 2, and you will get 0.4 as our probability. Or you can actually see 40% of the entire rectangle lies between 8 and 10. So with the uniform distribution, all you really have to do is take height times base to get probabilities. On the third part, I asked you what's the probability between 8 and 11. And I told you to be careful, and the reason you want to be careful is, remember, nothing exists above the point of 10. There is no probability beyond 10. So 8 to 11 is exactly the same as 8 to 10 was, and we just did 8 to 10 a minute ago on the second part. The answer again is 0.4. So you still have a 40% probability. That's really all there is to a uniform distribution. Just remember, if a problem tells you that it's uniformly distributed, it just looks like a rectangle. You can figure out f of x from the formula 1 over b minus a, and then you can figure out probabilities by just taking height times base. That's the end of part 1, and in the second part, we're going to start into the normal distribution.